All right, welcome back to Mechanical Systems Design. In this video, we'll talk about assemblies, and we'll focus on how the way that parts fit together can influence their loading and expected errors. As always, it's best to read the topic reading carefully first, and we have a bunch of great worked examples in there. And we'll do a few exercises at the end here, so it'll be nice to have a pencil and a paper, and if you can connect up with somebody to do these together, that makes it a lot more fun. All right, so assemblies. We need assemblies often in mechanical systems design because we might need two pieces to move relative to each other. We might have complex geometries that are not well suited to manufacture out of a single part, or we might want to use multiple materials, or we might be concerned about maintenance or repair or portability. So there's lots of reasons that we might, or adjustability even, we might want to take things apart or make something out of multiple components. But of course, as soon as we have multiple things, it introduces a bunch of new challenges. Generally speaking, the more complex our system is, the more opportunities for error there are, the weaker it will be, the heavier, and the more costly. All bad things, but sometimes we can't get away from it. We're going to focus especially today on force and error multipliers, which will emerge as we we make a structure out of multiple components that are connected together at a few points. And also we'll talk about induced loads. So first we're going to just review a few of these concepts from the topic reading. And the first one I talk about is what kinds of forces that we get at the connection points in our assembly. And one choice to think about is that between normal loading, shear loading through shear on a pin, and shear from friction. So if we consider this beam that we've split into two pieces, on the left here, we've added some flanges and some screws. And when we push down on this end of the beam, what we'll see is that a free body diagram will show us that we're going to get a compressive force down here, and this screw will be put in tension. And screws and bolts are generally designed for axial loading like that, and so our screw will be pretty happy. And these two surfaces pushing together are going to be quite strong. So this loading scenario, it requires a little bit more complex geometry, but it tends to result in a relatively lightweight, strong assembly compared to our options on the right-hand side. So let's say instead we break this into two pieces, and then we have an overlapping section. We call this a lap. And then we put, say, a through hole on one side and threaded holes on the other side, or we have two through holes and a bolt with a nut on the other side. So if we loosely tighten our screws or bolts, or just put some pins in there, we'll be loading those screws and bolts theoretically in shear, more likely in real life in some complex bending. And our fasteners aren't designed for that. They generally don't like that. And that's going to be a weak point. We need much bigger hardware for the same transmitted, for the same reaction moment at this connection. So a better way to do that, if we needed to use this kind of approach with a lap, would be to tighten those screws or bolts tightly so that the two pieces press against each other hard. And that generates a normal force, which can allow for a friction force. So instead of generating these horizontal components of force that we need from directly on the screw, it's the two plates pushing on each other, and they can generate a friction force like that. But the qualitative loading is now a lot better here. But notice that in order to generate sufficient friction force, because the coefficient of friction is usually less than 1, our bolts or screws are now going to need much higher force in this scenario than in the one on the left. And notice also that in this case, the way we have it, the distance between the two holes is a little smaller than over here, and that would also result in a higher reaction force. So if we can get away with it, we'd prefer to choose a normal force over friction or shear. Another thing that we might want to think about is whether we have reaction forces or moments at our joints. As we just saw a moment ago, uh, when we have that beam that has a bending moment in the middle and we load it, um, we need these two opposing forces at the joint in order to create this couple, this force couple that creates a moment opposing the applied moment. It's much simpler if we can just react out one force at a joint. And we saw in our, we talked about this a little bit when we, in the topic reading when we discussed why are triangles strong. And, but in this triangle shape, what we get is we see that if we do our free body diagrams for each link, we can have a scenario where each reaction is just one force. And so at each of those joints, you could have two surfaces just pushing on each other. And we wouldn't need the connector hardware to be in tension or be tightened too hard. On the other hand, if we look at this square scenario, if we do our free body diagrams carefully, we'll see that no matter what kind of assumptions we use, at least one of these joints is going to need to have a moment. And so if we think about what that means for, say, link 4 here, where you have this reaction force that's basically orthogonal to link, it's got a big lever arm, so it's going to generate a big moment. And then that moment has to be reacted out in this joint somehow. What it really means is probably that we're going to have a couple of forces that are in opposite directions, but their lever arm relative to each other has to be really small because this link is pretty skinny compared to how long it is. So there's going to be a big force multiplier. And that means we'll either need some massive hardware in there or we're going to have a weak joint. So another possibility here would be, say we have a lap and we have one screw or bolt going in there and we tighten it really hard. Okay, well now we have this contact patch and we will have friction, and that friction could give us some of this like scrubbing friction to react at the moment. But there again, the lever arm of some little patch of friction relative to the center of rotation will be really small. So we're going to need a huge friction force and an even bigger normal force caused by tightening that bolt to get that to work out. So if we can avoid it, we'd like to not have big moments at our connection points. Okay, another odd phenomenon that we talked about is constraint induced loading, where many times we think that if we add more connection points, things are going to get stronger, but it's not always the case. What really want to do is add just the right connection points. So we get a perfectly constrained system where we know exactly what the forces are at each point and that they're nice and low. So here's an example of a situation where we've added an extra bolt here or screw, but because of manufacturing errors, this is actually inducing bending in a component, and that will lead to bending stresses, which are quite pernicious, as we know. So this is something to keep an eye out for as well. The big thing for to look out for when it comes to loading that arises from our geometric choices in assemblies is force multipliers. And we talked about this a couple times already in our examples, but just to put a fine point on it, we can look at the case of our simply supported shaft versus a cantilevered shaft here, which we discussed in the topic reading. And what we saw is that if we do a free body diagram of the shaft over here, we're going to get a force of 1/2 of the load up on either side, versus in this case, where we have the cantilever, we're going to end up with 2 times the load up at this bearing and 1 times the load down at that bearing. And that's because this case on the right has a larger force multiplier. And what do I mean by force multiplier? I mean, you think about what are the lever arms that matter in the system. So let's say we're going to do a free body diagram of this shaft, and we pick, say, this is our moment balance point. This load force has a long lever arm about that point compared to this bearing. So this bearing force will have about half the leverage of this load force. So that is, the reaction force here has to be double the load. And if we instead do that same analysis over here, and we take this point for our moment balance, now the bearing has twice the lever arm as the load force. And so the bearing force can be half the load force. And that's how we get to that 4 times higher bearing force for this cantilever compared to the simple support. And that really matters in these systems. Bearings are often strength limiting components in these designs, or large contributors to mass or inefficiency. So this is something to really think about as you're working on your designs. What are the key lengths? What are the key lever arms? And am I inadvertently generating a really high force somewhere where I don't want it? All right, so that's a lot about loading. We also talked about errors or tolerances or slop or inappropriate placement of an element, a key element in your design. So one way this can happen is just through clearance or manufacturing errors. So here's a classic example. We've got a screw that will go through a through hole and a threaded hole. And the threads will probably have a fairly tight tolerance. The location of the threaded hole, that will depend on how accurate our manufacturing process is. But this through hole, we're going to need a gap in order to be able to fit the screw in. And that introduces some error. We're not quite sure where the hole will be relative to the screw, which means we're not quite sure where this top element will be, component will be relative to the bottom component. Compare that to our uncertainty in the total thickness of the two components once they are stacked together and that screw is tightened. In that second case, we only have our manufacturing error to consider. And so we have more certainty about this dimension than, say, the side-to-side location of these two pieces. Another thing to keep our eye out for is that these tolerances can stack. So let's say that we really care about the orientation of this bar here in our triangle. There are lots of different places where we can get some kind of error. So let's say we use pins in these joints. So we've got that clearance and some manufacturing uncertainty there. So maybe this point is a little lower than expected. Maybe this point is also a little lower on this right-hand side bar. Well, then in absolute space, that this displacement and that displacement would add. So the maximum possible error in location of this hole would be 2 delta in that direction. And then if we think about what's happening in here, well, we have the exact same thing. So this one could be up and to the left by 1 delta. So effectively, we get this relative displacement, that the maximum possible relative displacement of that top point relative to the lower left point is 3 delta, right? So you could get a pretty big angular error even with fairly small expected errors at each joint. So that's the idea of stacking. Error amplifiers are another serious issue to look out for, and they work very similarly to force multipliers. The idea here is that if we do a geometric analysis, we've got some long length and some short length that's associated with the error. So that if when we're manufacturing this component, there's a little bit of a bump here, or there's a little bit of less material than expected, so the surface isn't quite orthogonal to the other surface, then that can place this thing on a bit of an angle, and then this distance that we really care about can be much different from what we had wanted. And here the error multiplier term or amplifier term is this length divided by this thickness. So we want to figure out what those are and try to keep the multiplier small as is practical. All right, so those are a few of the things we talked about in the topic reading that we want to consider when we're thinking about how to put together multiple components. Let's do a couple exercises. We're going to do 3 exercises today. And the first 2 are break it up exercises. So what we're going to do is look at a single component and say you're forced to break it into an assembly of multiple components. And you can imagine a reason for this, like you want to use a cheaper manufacturing process or something like that, or you need it to be disassemblable for portability, or in order to put something, in order for it to be able to fit together some other components that must be separate. And what we'll do is we'll have you generate some candidate assembly ideas and then analyze them using either free body diagrams or geometric analysis, looking for force multipliers or error amplifiers. And then you're going to look at the results for your analysis and think about what they tell you about how you could make the assembly better. Maybe which parameters should be big or small, and maybe it'll give you insights into qualitative changes in the assembly that would make it more effective. And here's our first exercise. So here we have this support structure, a yoke that's holding 2 bearings. And it's connected somehow to some support structure. And this is the component that's got the top left to bottom right hashes that we'd like you to break apart. Now, there are going to have to be some changes to the geometry. So you have to, allow yourself to be flexible and massage the overall shape, but the general shape should be pretty similar when you're done. And what you should do now is, one other thing to think about here is we've got bearings that we're supporting by this structure. And something you know about bearings is that they don't tolerate a whole lot of misalignment. That if the shaft doesn't come through relatively straight along the axis of the bearing, then you'll get undesirable contact and wear. You might load the ball bearings inside the balls inside a ball bearing with some axial components that might damage them. So you really want to get those bearings well aligned. So let's focus in this exercise on the alignment of those 2 bearings. Okay, so take out your pencil and paper and sketch 5 or 10 different ways of breaking up this component into an assembly. And that should take a little while, 5 minutes or so. And take your time, be patient yourself. And then do some analysis. In this case, since we're worried about alignment, do some geometric analysis. Think about all the different ways that there could be initial errors due to clearance or manufacturing errors, and then how they'll translate into error in the position and orientation of those bearings. And do that for one candidate design that you think is most interesting. And then after you've done the analysis, take a step back and think about what it really means. And you can then come up with a new candidate design, or just think about write down what kind of relative dimensions you'd like to see, and go from there, and then come back. So this would be again a good time to work with a partner if you can get in touch. And this whole thing should maybe take 15 minutes or so. So hit pause now, and we'll see you in a minute. All right. Did you come up with some good designs? It's fun. There's a lot of creative different ways of breaking things apart to perform a really similar mechanical function. So I hope you had fun with it. There are lots of different ways, but we'll just talk about a couple. So here's a common solution where we've taken this thing and broken it into 2 side plates and 1 horizontal plate. And then we're connecting that vertical plate to the horizontal plate by putting, we've got some through holes in the vertical plate and some screws that are, say, threaded into that horizontal plate. And the strength of this design is that it's very simple. You have these planar shapes almost. Certainly the vertical elements are planar. So they could be manufactured, say, by laser cutting or something. The horizontal element will need some threaded holes, so that's a secondary manufacturing process. It adds a little complexity, but still fairly simple overall. The downside is that by coming in from the side like that, we have this clearance to get our screw in, and that means that our bearing can move. We have some translational error in its location, and then the axes of our bearings may not line up exactly the way we'd like. So that's the downside of this approach. And another thing that can happen here that's a little harder to see in this picture, but is a little clearer for this similar approach, is that we have this this error amplifier. So in this case, it's similar to the previous, but we're coming down from the top through the horizontal plate. And in this case, we've got this long vertical plate and this thin section where the two plates contact each other. And the critical distances here are, this long thing and maybe half the thickness of this vertical plate. And that becomes our error amplifier, L over, say, 1/2 T or something. And just taking a look, that's going to be a big number. And so a little bit of manufacturing error or something like that here is going to lead to a pretty big error in the angle of that plate and the axial location of the bearing, and also possibly the angular orientation of the bearing. So, and we've seen stuff like this in our project 2 components where we a little bit of defect in that surface would cause the thing to tip in some undesired way. So it's a similar thing. Here's another example of how we might do this. And in this case, what we're doing is we recognize that this distance, it is the critical dimension for reducing the error amplifier. If we make that big, then the denominator gets bigger and then our amplifier gets smaller. So that's the general principle here of trying to spread out that contact. And by using 2 screws, we're going to get good, we're going to be able to press those 2 components firmly together in a couple of more widely spaced locations, and that will give us better tolerance on our bearing location. Another thing that you could use here would be an indexing surface. So here we've manufactured this horizontal plate with a little lip that touches a vertical surface on that vertical component. So when you're assembling them, you slide these together before tightening the screws, and that means that we've eliminated that clearance error as well. So this is one way to do it. Now, the downside of this, of course, is that these components are more complicated than those in the previous part. None of these things would be manufacturable by laser cutting, for example. But that's the trade-off here, where you end up with better tolerances. Okay. The next exercise is, again, break it up. So here in this scenario, we've got some kind of support surface. We've got our element that we'd like to break up. And then there's some force over here. And our component is supporting that force. It's an upward force. In this case, we're not so worried about precision or error in exactly where that force is held in space, but we do care a lot about the strength and mass efficiency of our structure. So for this one, let's focus more on force multipliers than error amplifiers. So once again, get out some paper and a pencil, sketch 5 or 10 different possible ways of breaking this system up. And remember, when you're generating candidate designs, you want to try to generate things that are qualitatively different, but while staying as simple as possible. So as you try to generate new different designs, think about what are all the different simple ways of breaking this into multiple pieces. And so sketch that out. That should take 5 minutes or so. And then Pick one that you like and do a free body diagram analysis. Try to figure out what is the force multiplier. And that should take 5 or 10 minutes. And then take a step back, look at your analysis and think about what it tells you about what dimensions should be big, what should be small, and maybe sketch one more final candidate design that embodies the lessons you learned from the back of the envelope analysis. So the whole thing should take about 15 minutes and take your time. All right, you should hit pause now. All right, did you come up with some good ones? Here's one that you might have thought of. So this is really similar to the last example from the third example from the last exercise, where we have some vertical plate and a horizontal plate, and then we have these 2 screws connecting the two. And that means that we can get this distance to be a little bit bigger than if we just had 1 screw coming from the side. And just like with the error amplification, the reason it matters here is because of the relative lever arms and how that affects the load multiplier. So here's our free body diagram, and you'll notice that we've got this vertical force from the applied load. Oh, and I'm missing a vertical force over here as well. That should be equal and opposite to the applied force, maybe generated by friction from the contact between the 2 components. But the thing that I'm really worried about is that this applied force is going to create a big moment about, say, this point over here. And this length is a lot bigger than this distance. So we know that if we do moment balance here, the force from this screw is going to be L over D times the applied force. And I'd like to make this displacement bigger, but I've had to add this lip to the part, and making that really big might be, might run into some manufacturing challenges. It might introduce some bending in this little leg. So a very closely related way to do this would be to say add a 3rd component. So here we have this top element is really simple again, with just some through holes. And we've added this triangle to go in the corner between these 2 plates. And that helps because we can get a bigger displacement between the contact force up here and the screw force down here. So the denominator in our force multiplier can get bigger. And actually, maybe we can get it even bigger. This is a free body diagram of the combination of these 2 components. Remember, we can do an FBD on any combination of parts that we like. But maybe we because this triangle is a separate part, it's easier to make it bigger and to get a bigger displacement. It's a little detail to think about here. Oh, we also get this vertical force from the screw to react out that applied force, and there's some indexing going on, which is nice. But a little detail to notice here as we think about the forces here. You'll notice that this force I've called FC for the contact force, and I've located it really close to this top corner. And this F screw here, we're calling it F screw, and we're locating it closer to a little offset from the corner. And the reason is that this screw force is meant to represent the sort of average of all the force, the pressure from those internal threads in the triangle component. And so it should kind of be along like this line. Up here in this example and in the previous one, we can see it in the previous case as well. Sorry, having a little trouble changing slides. If we try to compress that screw, it won't produce any force. It'll just slide back out the hole, right? So this force at the top corner here isn't coming from the screw. It's coming from the 2 surfaces pushing on each other. And in the real system, that pressure will be distributed over some finite region. But the very best case would be that it was all concentrated right at the top corner because that gives us the biggest displacement between the two. And it's the same thing here. So this might be a slightly generous estimate of what that distance between the two forces is. Okay, one more example here. And this one we call holes in space. So I was an intern 20 years ago in a robotics company. My great supervisor suggested this way of thinking about assemblies as you know that you want these components to be in these places relative to each other, especially true in transmission design. And so you really want a hole over here to contain a bearing or a shaft or something. And then you figure out where you want all the holes. And then afterwards you figure out what structure can connect them and create the hole. You need material around the hole. And you may run into this in your current project. So the way that we do this is first figure out what pieces you want and where, then do free body diagrams on those pieces to figure out what reaction forces you need at their connecting points that are floating in space at present. And then after you have those reaction forces and you understand what tolerances you care about, then you can think about what structures would connect them well so that you'd react out the forces against each other. And we'll do one exercise like this, and we'll do it for a gearbox. So here we have two custom gears. They're meshing. Each one is on a shaft, and each shaft is supported by two bearings in simple support. And so we know that we want these bearings to be floating in space at those locations. And your job is to create an assembly that will contain those things and connect them. So in this gear train, of course, we have a force between the teeth of the gears that will be important to think about. How would that load the assembly that we create? And the other thing to think about is that these gears need to be located precisely with respect to each other. They need to be parallel, and these faces need to be coplanar, and the distance between the shafts needs to be as close to what we'd like it to be as possible. All right, so once again, take 5 minutes or so, sketch out a bunch of candidate designs, and then take a step back, look at them, think about which one appeals to you the most, pull it out, perform some analyses, free body diagram analysis, geometric analysis for error propagation, and then that should take some time, maybe 10 minutes, 10, 15 minutes, and then look at what those analyses are telling you and see if you can come up with desirable relative values of parameters, or maybe even some new ideas for qualitative shape. All right, so you can work on that now. So hit pause now. All right, did you come up with some fun ideas? Here are a couple that have come up a few times over the years. So this one is a very straightforward, simple box idea. You have a gearbox, let's make a box. And once again, we have this benefit of very simple manufacturing, right? We've got a plate and a couple horizontal plates. Maybe you come in from the side with screws. But just as we saw in some of the other examples, the weakness of this approach is that it is more prone to errors. In particular, for our gears here, a little bit of error at these skinny little connection points will translate into a big error in the relative location of the two sides of the box, because we've got this error amplifier with this distance divided by that thickness, as we see here, and that can lead to some unhappy gears. We can reduce the maximum possible error by making a more complex structure, like a clamshell design. So in this example, we've got each side looks sort of like a C. This is a backward C. And then there'd be some screws connecting them together at these flanges. And we can see that if we have a little bit of manufacturing error, or we have some clearance when we screw these things together, the maximum error that will result is just equal to that manufacturing error. There's no multiplier. And we could even get rid of that if we add some indexing lip in this design, such that maybe the right-hand side always fits inside the left-hand side, and then we are left only with the manufacturing errors, and actually the fact that it goes all the way around helps reduce that even more. Now, of course, this is a more complicated part, so it's maybe more expensive. It may limit our manufacturing choices, but it will result in tighter tolerances. Now, if you look at the free body diagrams for this, what you're going to see is both of these designs have the strength that those side plates are have a good overall shape for, say, torque in that plane, or say 3-point bending or things like that. Depending on how some other element was attaching them to torque those gears. So what we can see is as we start to break things apart, there's lots of ways, lots of new failure modes we have to consider, and especially thinking about force multipliers and error amplifiers will be important. But with the use of free body diagrams and a little bit of geometric analysis, we can make our assemblies strong and precise. So hope you enjoyed this, and if you had some assembly ideas that you generated during the exercises that you wanted to bounce around, bring those to the coaching sessions, and we'll analyze them together with you. All right, happy designing.